Assalamu alaikum, dear students. Welcome to Nuclear Physics lecture. I'm Dr. Parvez Ahmed. In this lecture, we will discuss the second part of the nuclear shell model. So let's move toward the second part of this model. And this part, we will talk about the spin orbit term. We will start the lecture from a basic question, that is, how does the spin orbit term look like? I mean, that is the basic questions, and our lecture will be totally based on the discussions about these questions. So, you know that spin basically we represent by the capital English alphabet S, and the orbital angular momentums by L, and our models are that of the single nucleons and the assumed average potentials. So, uh, in the middle, the two nucleons interactions average to applied potentials, and the two nucleon spin orbit terms average to 0. So it's reasonable to assume that the average spin orbit term and the strongest in the non-symmetric environmental near the edge, that is and that is the edge, and we say that these potentials, I mean, it's equal to 1 over r dv over dr. So for the detailed discussions of these potentials, that is, I mean, it's uh, that's why the way we are saying that it's reasonable to assume that the average spin orbit term is strongest in the non-symmetric environment near the edge. So for that, we have to do the calculations for the potentials, and for that potentials, you have to utilize some of your previous concept from the quantum mechanics. I mean, you people have studied different terminologies related with the angular momentum, related with the span, and that is being linked with the potentials. So you have to utilize that spin orbit coupling concept and the word sections models and word section discussions. I mean, you can see it here and you can watch by yourself. So that you have to remind, you people have studied that in quantum mechanics. So that concept you have to utilize from your previous knowledge of quantum mechanics, that is spin orbit coupling, by studying the Wurtz-Jackson concept, and then by utilizing that concept, you already know the value, some of the values in the nuclear physics. uh, that is, you know about the radius. We assume that radius being spherical in shape, so you have to utilize the value for the r naught, which is approximately equal to 1.2 pentameters, and the value of the d, which we utilize here in this word sections potentials, that is d is equal to 0.75 pentameter. That is, we assume that should be the thickness of the edge. So by utilizing all these values, you will reach to the potential value. But here we remember, we have the dimensions. So at this particular point, you know that the dimensions of length, and we compensate that 1 over r dy dr. I mean, this is been notified with the this arrow sign. So what we have to do next, I mean, you know that if you are expert in quantum mechanics, you people have studied in quantum mechanics. So a good quantum number without ls term, that is, we have to utilize l lz. I mean, these are the quantum number for the angular momentum, and span s is equal to 1 by 2. As the z component of the span from the operators l square lz, s square, and z component of the s with eigenvalues. So these are the eigenvalues for the l, and for the small s for the span, and so these are l into l plus 1 and 2 h cut square, smaller s into smaller s plus 1 and 2 h cut square, uh, Lz, z component of the angular momentum, h car, sz, h car. So these are, I mean, the angular momentum and the span quantum number. So what we have to do with Ls term, we need operators that commuting with the new edge. So for that, we get J, that is total angular momentum, is equal to L plus S, that is the sum of the angular momentum plus the span momentum plus the span, and the Z component of the total angular momentum is equal to the Z components of the orbital angular momentum plus span, Z component of the spans with the quantum number J, Jz, L, and S. Uh, since we know that S has the span has a value that is 1 by 2 or half, so one get J is equal to L plus 1 by 2 or J is equal to L minus 1 by 2. We know that for the half the span is positive and for half the span is negative. So in this particular condition you should know that L is not equal to 0. So giving eigenvalues of Ls, we can get Ls equal to L plus S whole square minus L square minus L square. So it lead to 1 by 2 into J into J plus 1 minus L into L plus 1 minus S into S plus 1 whole multiply by h cut square. So the potentials become, I mean, by doing all these discussions, we get the values for the potentials, which is V plus 1 by 2 L h cut square and W, and that is for the condition J is equal to L plus 1 by 2. And plus for J is equal to L minus 1 by 2, the potentials are the value, the potential becomes like this. So from here onwards, we can see this asymmetric splitting on slide number 16. So there are of course two well with different potentials for neutrons and protons. So we currently assume one well for all the nucleons, but the shape of the well depend on the size of the nucleus, and this will shape energy level as one adds more nucleons. So using a different well for each nucleus is too long winded for us through a perfectly double. So let's not use this model to precisely predict the exact energy levels, but to make a magic number and predictions for the shell models. That is, I mean, so what we get or what we can predict from the shell's model, that is total nuclear spin in the ground states. So the total nuclear angular momentum is called the nuclear span, which is equal to J with the subscript totals. I mean, that's how we denoted the total nuclear angular momentums. I mean, the total nuclear angular momentum we call nuclear span, and we denote that by English alphabet J with the subscript TOT for the totals. So just a few empirical rules on how to add up all the nucleons J's to give J totals of the whole nucleus. Two identical nucleons occupying same levels, that is same N J's or else couple their J's to give J pairs is equal to 0. That is J even ground states equal to 0. I mean, that is this how we do for the pairing. So the totals nuclear angular momentums, I mean, is for the odd number of nucleons, that is one unfair nucleons should be equal to J unfair nucleons. So we should be careful here, and that is we need to know which level nucleons occupies. That is more or less accurate shell models is being needed or wanted. So that's we have the modulus of the total angular momentum of unfair neutrons minus the total nuclear momentum nuclear angular momentum of the pair protons should be smaller than the total odd nucleons, which should be smaller than the total angular momentum of the unfair neutron plus the angular momentum of the unfair proton. So this is the fact one should remember. So there is no rules on how to combine the two unpaired momentums, and there is the unfair momentums of the two nucleons. So parity of a common system, that is nucleus. I mean, it's you know about the concept of the parity, and the nuclear physics, and you also studied that in the quantum mechanics. So here in this particular case, we will consider the parity for the nuclear systems. So this is how we have the conditions for the parity, and you know that how it's the parity of it's the nuclear system, that is atomic mass. We take a particular atomic mass and for a nuclear system, and we know that how the parity for the intrinsic nucleons and you know that how the parity is equal to. We took a conditions. We take the value of I. We say that I varies from 1 to that particular atomic mass, and then we calculate the parity. By utilizing that concept from the parity. So what we get, we know that the parity for even ground state should be equal to uh, plus 1. And why plus 1? Because all levels being occupied by the two nucleons. And we get the parity, that is or for odd number of the nucleons in the ground states. We say that is equal to phi for the unfair nucleons. So no prediction for the parity of odd nuclei. There is no predictions for the shell model has no predictions for parity of odd nuclei. So the shortcoming. What are the shortcoming of the shell models? So some of the shortcoming of the shell model includes has been the fact that we cannot predict spin or parity for the odd nuclei. It tells us that we do not have a very good model for the LS interactions. So a consequence of the above is that the shell model predictions for nuclear magnetic moments are very imprecise. So we cannot predict accurate energy levels. Why? Because we only use one well to suit all the nuclei. We ignore the fact that neutron and proton should have separate wells of different shape. So as a consequence of the above, we cannot reliably predict much, so configuration, excitation, energy, etc. About excited states other than an educated guess of the configurations of the lowest excitations. So that's all we have for the shell models. So just like the previous model, that is the semi-empirical mass formula liquid draft model, the shell model also have some of the shortcoming. So in order to overcome the shortcoming, the shell models and liquid drop models, the scientists really feel for another models which can combine the effect of these two. Some of the good features of these two models, and other to present the structure, the nucleus. The behavior of the nucleon inside the nucleus. So their needs. They strongly felt the needs for another model. That model we will explain. We will explain in the next lectures. So that's all for this lecture. See you for the next lecture. Till then, bye bye.